Good morning. I'm Robert Shear. I'm a research software engineer at the data science department at the Dana-Farber. My full-time responsibility is as a member of the bioconductor core group. Today, we're going to spend 2 hours for what I called the Quickstart for data professionals for RStudio. Let's look at the agenda. I've asked you to familiarize yourself with the first three chapters uh, of Ralph Irizarry's Introduction to Data Science online book, and also warn you that I expect that everyone here is got some experience with a high-level programming language. They know about variables and loops and programs and like. If you haven't got RStudio installed, that's okay. It's probably better if you can follow along. We don't, in 2 hours, we're not really going to have time for, any serious, workshop puzzles. But what I am going to try to do is and the purpose of the first three chapters of Roth's book were to make sure that you had a basic feel for what's where. What I'm going to try to do is to take the time and explore topics, some big and some very specific, that relate to things that I wish I knew when I was sinking my teeth into R and trying to transition from other technologies. So I think the first thing I'd like to do is just take a look at the user interface. And here it is. Oops. And let's forget about the fact that there's a bunch of stuff up here already. So here in the user interface, we have, and this is the user interface for RStudio. Let me step back for a second and say that we have four kinds of programs we're going to deal with today. The first is the core R package, which is a programming language, purposely built, designed almost 50 years ago for statistical computations, and remarkable because not only is it growing quickly and it is usually amongst the top 10 languages in the IEEE survey, but it's far and away the only language that is domain specific, that is statistical and data science based, that's anywhere near the top 10. And so it's kind of exciting that it's got this strong, this really sound foundation in the lineage of Lisp and Scheme, which are very foundationally strong approaches to programming computers on the one hand, and on the other hand, a statistical analyst who's spent her career in SPSS or SAS or Stata can walk up to it and after learning the terminology, apply most of their skills and act more or less as is. At any rate, so that's step one. Step two is let's look at the picture. Yeah, that's the R language. So that's one of the four kinds of software we're going to use. The second kind is RStudio, which is a product produced by a company formerly known as RStudio, now Posit. It's a PBC, a public benefit corporation, and they do have revenue producing products and they do make money, but they've done an extraordinary job of contributing to the R infrastructure and the progress of the R language. The third kind is packages, which are contributed by the community, of which 20,000 are currently available on CRAN. Well, some of them may be someone's master's capstone project, but many of them solve really interesting problems or provide alternate solutions to really interesting problems in the world of data science and statistics and specific. The fourth kind of software is just a very little bit of software that you and I will write over the course of the day. But let's go back to the screen. Can you see my my RStudio screen now?
Yes, yes.
So this is more or less, this is almost exactly what it will look like whether you're on a server based, with X Windows or X11, I should say, or a web browser with a cloud-based server version, or a laptop, whether it be Linux or Windows or Mac. It's divided into 4 quadrants, and I'm not going to spend a lot of time on this, but my idea is as I go along and as we explore some examples, we're going to point out where we've exploited one or another of the features of RStudio. So in the upper left-hand corner, we have the place where we'll do all our editing and we'll interact with programs we may be writing. In the lower left-hand corner, we have a console, which would be the way that I would write programs if I were, sitting at a command prompt. We also have a command prompt itself. In the upper right-hand corner, we have all the sorts of things that we can do with environments. I'm looking at the moment at, there we go. I'm looking at the moment at a place where we can see the variables we've created. I'm looking here at a complete record of all the stuff I've done this morning. These other things, these other tabs, and there may be more or less tabs depending on what you've asked RStudio to do for you, but these are all related to our environment. And in the lower right-hand corner, there is all sorts of information that's valuable to us, including most of our output, except for the output that appears here on our console. So that's that. And now, yeah, so easy enough. Oh, so look, I'm going to start with something that's, maybe you've seen this already, and feel free to stop me to ask questions or to point out a blunder that I may have made. But what I'm going to do is to take just a few minutes and do a mini example of more or less a demo of what maybe a student of statistics might do with RStudio and trying to go through a whole workflow from data set to conclusion. Now, and I'm going to do it with, and it's going to be right here. And all the script that I'm going to use is right here. This is I'm going to just start really from the beginning. I'm going to get rid of all the data that's there, or all the tabs that are there. And I'm going to go to this file. It's just a file. And it lives at tilde/project/RStudio Quickstart. And if I just push this run button, I'll run the whole thing. And that would make this a very short demonstration and probably unuseful. But one of the things that is particularly useful about this editing window is that I can execute one line at a time or several lines at a time, as if I had typed them down here. Another thing I should mention is that most of these tabs it's hard to see, but you see there's a little paintbrush here, and that's a whitewash brush or a cleaning brush. So that clears the screen. The library command makes a package available for immediate use. The pound sign or the hash mark, most of you probably know, is the comment button. And from that point on, from in a single line, it's a comment. This is a literal string, and this is an assignment. This little paintbrush is going to get rid of all the variables I have. And when I make that assignment, and I've done that by holding the command key and then pressing the return button. If I were on a Windows or a Linux system, I would hold the control key and hit the enter button. And by the way, I'll mention also that I don't know if you can see my help or not here, but there is a keyboard shortcuts help. Now, as you read through the parenthetically, as you read through Rafa's book, he makes the he wisely suggests that you memorize a number of these keys. But I think that's a really valuable idea, but I would caution you against trying to remember all of these as if you were learning a foreign language. Instead, as you go along, identify the things that your personal style allows you to indicates that you use frequently, and introduce those one at a time. Eventually, you'll pick up the pace without overloading your cognitive capacity. Now you see that I have I said I've assigned the variable, and I'm going to read this file. Now, this file came from I don't have a browser. This file came from a DOE, or probably a EPA study of a spreadsheet of that's comprised of a CSV that has cancer by site by for females in America by year. I push that button, and there, and I have read in the entire spreadsheet. I've told it to skip the first 5 lines, and the title should be on the next line. And let's take a peek at it. There's a couple of ways to take a peek at it. One is, oops, sorry, it's this one. One is to click this button. And this is the raw data as it came in and is transformed into a data set. Data set is probably a data frame, which is like a data set in, say, Stata or SPS. And that is columns. In this case, they're set up to make it easy to, to view, but not to manipulate, and a year of diagnosis. There's another peculiarity here in that there are nulls. And the reason these nulls are here is because if you go and look at that web page, there's a discontinuity in the methodology of cases per 100,000 between 1998 and 1999, and so this is kind of a hack that let them put a break in the image. But we're not going to do that because we're going to do some manipulation of it. So,
Robert, could I ask you a quick question?
yes, please, sure.
Just for the audience, you're just demonstrating, or did you want them to load this data set?
Yeah, this one, sit back and relax. You can fiddle if you'd like. You can sit back and relax. If you're listening to the recording of this, feel free to press the fast forward button.
Okay, thank you.
But yeah, I'm sorry, I meant to emphasize that. As soon as we're done with this, we're going to build up a data frame from its component parts. And there, you're more than I would encourage you, if that's your learning style, to follow along with me at your keyboard. If you don't, because you're more of a conceptual, or you learn better with your hands not moving, that's fine with me too. This I'm not even going to, this is something that I hope an hour and 15 minutes from now, you may be able to, you might be able to interpret, which is going to take this, I should have left that data frame here. Right now, as I say, I've got some number of sites, and not really diagnoses, they're sites, you know, in the sites in the human body, and years from 1973 to 2000, I guess 17. I want to get rid of the ones, just for our purposes, I'm going to get rid of the ones that don't, that are before 1999, so we don't have, we don't start a journey with the data that could be objected to. Performing that function, there we go, we said at 1999. But I still have a wide table, and I want a long table. Now, there's different ways to do this, but over the course of the life of R, a number of really powerful specific packages have been created that do most of the work that we need done. And so if you find yourself when learning R, doing lots of specific data manipulation of the sort you might learn in, you know, software programming course, you may not have looked hard enough for a function that does it. And this is a function. All functions start with an open parentheses and with a closed parentheses. We'll talk about the different sorts of things you can do today. But what this reshape function will do, will take a wide function and make it a long function. Or that could say direction equals wide, and the rest of this information would be appropriate for stretching it out. Again, fewer rows, more columns. Let's see what happened just there. Oops, I'm going to have to, it's a different, yeah, I gave it a different name. And lo and behold, we really only have, we have three, oops, I sorted it. We have three columns, year of diagnosis, and cases. That's per 100,000, as it were. This, you can ignore this for now. It was a characteristic of the reshape function that every row gets a name, and the name was constructed so that to make it unique. But we can forget about it for now. I'll just and let's continue with the. So what happens if I'm going to just clean up the names a little bit. Year and DX, so it'll make it simpler to see. And I'm going to more or less normalize the names because I've created, darn it, the wrong one. I've changed the year so that 1999 is year 0. And that's because I plan to do a little teeny bit of statistical inference. I'm going to do one other thing that you'll see, and you'll see why later. I could have done it up here in the read CSV, but it did not know that the cases should be numbers. It probably didn't know that because of the line of nulls that was in it, the original. So let's make sure they're numbers. What are the alternative numbers? You'll find out in just a couple minutes. Well, let's do something interesting finally and plot it. There we go. Here's the plot screen. Sometimes, by the way, you'll have to, when you say plot, it doesn't switch to the screen. It depends on how the environment's set up. And it'll be there, so be sure to click plot, the plot tab, if you're over here in help or files. Now, if we take a look, and there's a couple things we can do with this besides take a look at it. One is to look at the big picture, so to speak. And another one is to prepare it. Can I get that back? And another one is to prepare it for export, either as an image or PDF. I got all sorts of choices for image, and this is kind of a nice way to get started with preparing a figure for some sort of report or even to submit for publication. I get the aspect ratio I want. You see that it cleans up the text and symbols. And then if you press save, one of the nice things about this is we can use things like EPS SVG. So we could put this in a format for post-processing if you're trying to get something of really high quality for publication, for example. And if we leave it here, we'll be able to go back and forth. Oops, that was something I was fiddling with earlier. Back and forth. But if we look one more time at this, oh, you know what? What I wanted to show you was one little thing, and that was this. That's what I get for fiddling with my stuff. The way this showed up on the site, on the EPA site, was like this, and it was very clunky down at the bottom. It was like, what's really there? What's happening down there? And it was shrunk a little bit, so it was like, what does that all mean? And so what I did was simply add a log 10 scale to it, which exploded. It doesn't tell me how many lives were lost, but it does give me a better idea of some really interesting divergence between progression and cancer rates over time. Here's one final thing we're going to do, and then if your fingers are a little itchy, we can start following along. Here is an example. LM is one of the very simple of a large number of statistical functions you can apply. This is one of the simplest. LM. If we want to know what it stands for, what I'm going to do right now is press F1 while I've highlighted it, and I get to help. This is just about for anything. I could even I think I can press F1 on this assignment statement. Oops, there we go. I guess not, but anyway, there's another way to do that. But and there's all sorts of information on what you can do with fitting linear models. One of the really interesting things I said before that without going into any detail, R is a derivative of the scheme language, and this is not an expression like 1 + 2 = 3. This is a formula that represents the model. And the asterisk here is not multiplication. It means consider both variables and also consider the interaction. I could have written equivalently as dx plus year plus dx : year. Why? And that and cases, of course, is the dependent variable. And all I had to say was that the data comes from something called df. And I got the answer. Now, what about this? Well, I kind of got the answer, but let's take a look here. I can say print x, because the answer is in the variable called x. Did I actually run it? No, I didn't. Let me run it. Okay. I can say print x. And, oh, I've got so many different kinds of cancer. I could probably trim those out. But I can say summary of x. And by the way, here's the estimates, all the coefficients. Perhaps I shouldn't have. Let's see. Let's just change it to plus year. And try again. So if I say summary of x, I can go down here. I'm on my up arrow and down arrow key work. There, that's a little bit easier to read. And I can see my the coefficients for the linear regression. Now, I can also plot it. If I plot this variable x, it will provide some useful diagnostic information. I'm going to do one other thing first. I'm going to, and there's some cryptic stuff that you're going to have to learn over the course of time. And this is just going to say, I want you to plot, when I plot something next, I want to have 4 plots that are 2 across and 2 down. So let's go ahead and just say plot x. And there we have some peculiar diagnostics because it's a peculiar data set. And I guess we probably, given the QQ residuals, we probably did the wrong thing. I will point out, by the way, that there is a data type called a time series. Anyway, end of tour. I want to go back to the beginning and talk about, well, in Rafa's book, you may have seen 1 + 1, 1 + 2 = 3, 2.3 times 0.45. That wasn't the numbers he used. It's a number with some decimal places after, some digits after the decimal place. We can say hello. We can also say 1 + 2 = 3, and we come back with a number with a value true. These are atomic data types. There are 6 in R. Don't worry about, there's only 3 you should worry about today. And they're numeric, character, and logical. Logical, as we saw, is true. Shoot. Gotta be careful when I touch this keyboard. Logical is true or false. Numeric are 64-bit floating point numbers. If you are an experienced Python program, you sure, because they're not unlimited number of digits to the right. They're more of like NumPy than they are like Python. There is an integer type. Integer type is value. It's typically a 64-bit number, and it's useful for performance as well as for speed as well as memory usage. It is, however, not. You don't have to worry about it much. The only reason I really pointed out now is because you see 0L minus 400L. Those are integers, not numerics. They'll be automatically converted to numeric if they appear with numerics in the computation. So that's pretty simple. It's pretty simple if you program, and I think you all do program something. So far, so good. Any questions at this point, or shall I continue on? Let's keep going. Here's an interesting thing. When you first see those, they all look like scalars, but there are no scalars in the R language. The R language is inherently a vector-based language. The things that you saw that appeared to be scalars were in fact vectors of length 1. Now, vectors can have a length of 1 or any number that you've got room for in your computer, well, up to 2 to the 64th, I guess, 63rd maybe, and they can also have a length of 0. Which means that if you try to operate on them, nothing good will happen. You can create a vector arbitrary length of default values by saying, well, for logical of 1, give me a single value fault. It's probably the lowest possible value. If I have 100 of them, there's 100 of them. If I have 100 numbers, I'll have 100 zeros. Numeric. There's my 100 zeros. And as you might imagine, and I say these are called characters because the word string wasn't in common use back when they were defined. But if we say character, what do you think we're going to get? If you guessed string, you're right. Or character, yeah. I can combine the length of if I say x equals 1 or 12, say. Again, this is a assignment statement. Up here, we see that the x is 12 now. It's no longer a complex thing, and it says numeric, just as we, and if we said just, for example, 10L, now it says integer. If I'm kind of keyboard, I'm going to do all my work on the keyboard here. There it is. It's integer size 12. I mean, integer of the value of 12. And if I have C for either combine or concatenate of x, and 23, and I'm going to put in a integer, put in 4 zeros at the end. 4 zeros, all of which are integers. I say that that's y, and I see here that y is no longer its length is 6 as I expected, but it's not an integer, it's numeric because this is a numeric, and so the integer gets coerced to a numeric. That's about all there is to it. I'm going to just point out, I'm not going to waste your time. Most of this stuff you know. The equal to is a double equal sign. You will see one thing that you will see occasionally is instead of the assignment operator, instead of being a left arrow as a digraph, you see that as an equal sign, which actually works, which was not a great idea because it produced an unnecessary. It was an attempt to make it friendly for, I guess, for Java programmers or something, but it just confused matters. But it's still there. Try not to use it for that purpose. Now, so we can also build up sequences from the function called SEQ. So I'm going to take SEQ and we'll take a look at it. Here, sequence generation. I want to say a couple things. This is your friend, the sequence, the help. One of the wonderful things about this language is that every package, at least every package you get from CRAN or Bioconductor, will use exactly this format for documenting its functions. Usage, then arguments, then details, then return values, references, and usually available and useful C also. One wonderful thing about it, by the way, that is often overlooked is this thing called run examples. That didn't just display the examples, it ran it on my computer at this moment. When you're learning this system, you will find times that and even when you're an expert in the system, you'll find times when you've broken some underlying component and things don't work. More often when you start, there was a small blunder that you didn't recognize because you're still getting used to the symbols. And this verifies in one click that the examples that you see actually ran. So if I do that same thing, I take the same thing and I just copy it here. I should get the same. Indeed, I do. At any rate, and again, this forward and back works. I will warn you that in order to keep from repeating themselves, the authors of each pack, in order to repeat from, prevent themselves from bloating the documentation, put related functions together. So I want to see the value that's produced by seek int. I kind of will read through everything having to do with seeks and its cousins. But again, your friend. So that's one way to get those are numeric. That's a valuable way to get a sequence numerically. Counting n:(m). This is equivalent to counting from n, the starting value, to m, the ending value. It is only superficially like the n:(m) in Python. So don't try to transfer your Python knowledge if that's your current strong suit. And then finally, you can name elements, which is pretty nice, especially if you're doing statistical analysis and it's not everything is ergs per cubic meter or something. You subset vectors, which would be atomic vector, all vectors, but atomic vectors here, with by giving a number of them, the number, and the number can be a single number or it can be a vector of numbers. These are the same vector. And so here I should get that number, the second and third element of a variable var will be returned. Minus one, like what? Another this subscripting is only superficially like Python. So don't think about -1 if you're the way you think about it as a Python programmer. The minus sign indicates that everything except this subscript. So if I put a minus sign out here in front of the C, so I'd apply the minus sign to both the 2 and the 3, it would return everything except the number 3. If, for example, I wanted to return the last item, it's a little bit slightly clumsier, so I'm going to say x equals 1 through 10. X, and I can say length of x, and I can say x of length of x. Oops. I get the last one, and I go minus 10. I don't get the last one. I get the first 9. Okay, that's a lot of talking. So far, so good. Questions, feedback? No? Okay, let's move on. So here's the Boolean operators with atomic vectors. They're as you'd expect, except that there is a place where the binary operators can either return vectors or not. And vectorized operations can either can be reduced to a single vector. And the reason that's super important is because that is the key to filtering. I'm going to take this one. X is greater than. Well, we'll just take this x that we've already got. X sub. First of all, let's see what happens when I say x is greater than 2. No, it's greater than x, always false. X is greater than 2. It's false for the first 2 and true for the remainder. So the filter, x is greater than 2, takes the elements greater than 2 in this. These after here, where did I put this on? logical operators operate both on strings. They operate on strings and numbers and logicals, aka Booleans. The Booleans, the Booleans, by the way, turn into zeros and ones if they're converted to integer or a number in the style of algebra. But it's really useful in R because I can do a sum to find out, to count the number of true values I get. I can do a mean to find out the density of the expression evaluated expressions that are true. There we go. And now, darn it, there we go. There are some special values. NA means missing, basically means missing data. So this vector that's got a 1 and an NA and an 8, it's a vector of length 3. The second value is missing. Indexing the 3 will get the third value will give you an 8. A null is returned. It's like a perfect vacuum. It means there's certain things that never return a value at all. For example, a for loop, and so it's ignored when you combine vectors. Now there is a just to get your thinking clear on it. There is a function called append, like append in various languages that manipulate lists, but it's really kind of meaningless. Why? Because that vector 1, the first element 1 could have been, it's a list, it's already a vector. So for example, I say C of 1 comma 2 comma 99. It's just it's still a vector. It's idempotent, so to speak. So this null thing can get you in trouble because you're trying to have a nice square. You're trying to keep your data in order, and you have missing data, and it ends up getting turned into null. You're in a jam. NaN means a conversion to numeric fail. It's a kind of a special case, and it might mean that you've got a defective computation, or you've got dirty input data that you thought might be numeric, but not in dividing by 0, because dividing by 0 will give you plus or minus infinity. That's about now. There's one more kind of vector, and it's called a list. And the list is a generic vector, can take anything. Here's a picture of the vector Z created by list of X and Y. And we happen to have named these. And so this could be ragged, it could be complicated. We go back and I can store really sophisticated stuff in there. Many of the computational tools that you use as functions that do fancy things, whether it's some kind of regression, or maybe it's a bootstrap, or Bayesian inference or causal inference, they will store complicated lists that can be retrieved and operated on to perform a useful statistical computation on the results of the original analysis. Finally, the data frame, which no matter what language you're in, is if you're a statistician, is kind of home base. I'm going to go back and show you one more thing. So yeah, cases by variables. And it's a list of vectors. Under the covers, it's a list of vectors. On the surface, it looks like a matrix, except that the variables in our world have to have compatible, identical types, which is pretty convenient when you're computing. And so this structure of vectors list of vectors is quite useful. Now, we're going to give you one example, and then we're going to take a 10-minute break. During that 10 minutes, I'll be here. So if someone wants to ask questions or complain during the break, that's fine. There are numerous built-in example data sets in R. And some of them are famous data sets from the statistics books from the 50s or 60s or 30s even. And some are just useful, just useful. If you use the word, if they are present, and a number of them are available in the base R package before you loaded anything. And I think double question mark here, by the way, says don't go to something called data set. Tell me all about data sets. And here's everything about data sets. If I say vignette, and because I don't know how to type very well, I wanted to point out that we do have IntelliSense, which can get you into trouble if you're in a big hurry, but can also save you a lot of time. Data set. Oops, data set. Package. Darn it. Equals data sets. Sorry, I did that wrong. That's not how you find the data set. Data sets, colon, which data sets gives me the name of the package that qualifies it. And then I'm going to start typing in formaldehyde. I can learn about the data set. If I say data formaldehyde, it takes it from the library and creates a variable of that name. Finally, it says promise, and promise means you'll see this occasionally. You don't have to worry about it, but for really interesting, for really valuable reasons, computations are frequently deferred until they're needed in the R language. It's one of the things that makes some of the very fancy statistical computations possible. Now, if I type formaldehyde, again, I just tab to get to the end. It turned from promise to data frame. And here's my data frame. It's pretty modest. If I say plot carb.opt-den data equals formaldehyde, I'm going to get a very, oops, it's not carb. It is carb. Opt. I'm not going to do it that way because I'm not going to, if I say plot formaldehyde $carb and formaldehyde or that, and that's how you get into trouble by typing too fast. Formaldehyde. Look at all those things that start with for. Opt-den. This plot will see two vectors of the same length and plot them as X and Y with points. I'm doing something bad happened. So I'm not going to, so instead of doing that, I'm going to declare time for a break, and I will fix that before you come back. And again, if anyone has any questions while I'm, while we're gone, I'll stick around. And it's 10:51. We'll start again at 11:01. I did something kind of wrong here. I'm not quite sure what it was, but I do want to tell you that one of the things, just a tip, by the way, up at the top here, there's an ability to it's a session restart R. And what that's going to do is going to reset all the packages that are loaded. So, and then what I'm going to do is to wipe out all my variables. Oops, I want all the variables be wiped out. Come on. And all these things, there we go. All the variables. Oh, all yes. And now I'll start from a clean slate. One thing that can happen is that you test, you debug, you evolve, you've loaded certain libraries. You say, I don't need that library. I've changed the name of this variable. You've got everything working perfectly. And you come back in tomorrow morning and RStudio has resurrected your part of your environment, but not all of it. And either you have a package loaded, so then you go home for the weekend, you shut off your computer, you come back, and cannot find a function that you were certain you were using, or cannot find a variable. So it's really a great idea to start from a clean slate whenever or frequently. Parenthetically, one of the reasons that I advocated that you take a look at Rafa's Introduction to Data Science is not, it's a nice story, but I suppose that's an old story for most of you who are professional statisticians or analysts, but he also had a fair amount of personal advice on practice of programming with RStudio and programming the kind of work that we do here. And I think most of it's pretty valuable advice, and where there's differences of opinion, why not follow the lead of the people who are setting the tone for the department. At any rate, so that was my theory. It's somewhat practical. You're not sharing the screen. I'm still sharing. Am I still sharing the screen? I hope so.
Yep, you are.
Okay, great. So enough of that. So we're gonna just do a really quick review of. Actually, before I do that, I'm going to go back and we're going to do one or two more things with this data frame. First of all, I'm going to say data. Oops, I'm going to say this time DF for data frame equals data. That's formaldehyde, and there it is. Oops. What? Oh, is I want a data set named formaldehyde DF. What? Data. Data sets formaldehyde. There they are. DF equals, I don't know why that happened again, but here we go. So there's our, and there's our data frame. And the data frame happens to consist of a list of two vectors. If I say DF $carb, we can see it's popped up with this vector of six numbers. And we can also just say plot DF. Plot's pretty smart. It's going to know that it's looking at an object with 2 columns and 6 rows. Now they're kind of pseudo columns because they're really 2 lists. But there we have it. And there we have the points. Finally, if I say type equals L, that's a line that actually connects that pretty linear data set. And then finally, I can say something like as matrix DF, I'm going to say M is assign that to M. And now it looks the same, but it isn't. Because if I say structure of M, darn it, it is. It outsmarted me. I wanted to say as matrix, we'll say that was a bad example. Anyway, but it is a good example in one way. One of the things that is a little bit tricky about this language, and you will see it to a great extent in functions, is frequently in functions, is it will take defaults so that that statistician who we're talking about, who's trying to learn enough about R so he can view his colleagues' work, even though he lives and breathes SAS, that he'll be able to do things without a bunch of parameters, and that leads to certain defaults. I'm going to skip what they are, but you'll have to learn them over time. But I do want to get through some other things about the language. Well, scripting is almost just a file that's pouring in lines of code like the lines you've entered. If you're really new to there's no offside rule. What does that mean? It means that you can have as much or as little leading space as you want. If you have one tab and the next line has 4 spaces, you don't get an error it doesn't appear to be a new block. It's blocks like C and in Java and many other languages that existed before the offside rule became popular. So, and all it is and a block is either the end of a line or a bunch of stuff wrapped in a squiggle bracket. If we go back and take a look, X equals 1, Y equals 2. That's a single line. So, and here I can see there's my X and Y, 1 and 2. And I can also say X equals 1, X equals 3, Y equals 4. And I don't need a semicolon semicolon only if I'm on the same line. And then this little plus sign means I'm continuing the same block. Z equals 7. Oh, still continuing the same block. Close the block. Oops, there's X, Y, and Z as they were. If I use my up arrow to go back here, I get them one at a time. If I look at the history, there they are one at a time. But I can, if I wanted to repeat that whole thing, I can put these lines here. I can highlight these lines. I hold on the shift key to do that. And the console means it's going to go down there for immediate execution, which it did, but or a source. Let's make ourselves a new source file. New file, RScript. And there it is from the source. Pretty convenient. Now, well, that block comes in handy when I'm doing alternation. So, for example, if I say it's if open parentheses something that evaluates to a expression to a Boolean, and by the way, everything evaluates to a Boolean. I think at least all the 3 that we care about. I think that's going to be full. It won't evaluate to a Boolean, sorry. It will evaluate to a Boolean if it is the single string true. There we go. If it is the exact string false, it won't. If it's a number, great. But if it's 0, it's false. And every time I'm sorry, but I should have said, when you see the thing at the bottom, it means I've held on the command key and pressed return, which will also be Control Enter. And there it is, non-zero. So non-zero evaluates to as logical, 2, true, 1e minus 15, 14, a very small number, still true, 0e minus 14, 0, actual 0. Well, here's an important idiom. When we're scripting in R, we don't want to do that. You'll see almost all the well-organized R programs look like this, with one of a couple. So, and there I've held with command key down, return, run the whole thing. In this case, it's actually just like running the whole program. Boom. That also means I can say else, open parentheses, print. Oops. Print. I. It still says hello, but if I now say is 2 equal 3, the answer is no, and I get 5. So as a idiomatic matter, we use the kind of the original C version of these squiggle brackets almost exclusively, and that's really valuable in maintaining legibility. I don't need the I want to use the tabs to maintain the visual communicate the visual intent of the code, because I don't need it to specify the exact blocks. So where were we here? Oh, okay. So yeah, well, we're with functions. So we talked a little bit about functions, but there's a couple of things I really want to bring to your attention. First of all, there's the first of all, I'm going to go back here and say, let's take a look at mean. Question mark. There's a mean. It just takes a vector. It also has optional parameters. Trim equals 0, NARM equals false, and ... Well, this is not like someone who's waving arms and saying, and so on and so forth. It is instead an indication that that mean, if it detects that this value X is of a type that it knows how to refine, it will pass these arguments, any arguments here, back to the refined values, which in this case are date, time, and time interval. And likewise, trim is what? It is a fraction of observations to be trimmed, as in the normal description of statistical computation. And here's a really important one, NARM. If you have missing data and you in a vector, if you have even one missing variable value in a vector of numbers, the mean, all that entire vector will be coerced into the entire computation will result in NA. If, on the other hand, you want to ignore missing values in this computation of an arithmetic mean, you simply say NA.rm equals true. I can describe this either positionally or I can describe it with a keyword. So the NA.rm equals true here means I'm passing the argument true to NARM. And you find this particular keyword in a number of this kind of simple computation. The equal sign here means the default value is false. So I don't say anything. It won't remove the NAs, and everything will be NA. Likewise, trim should be 0 because I want to get the mean of the whole thing, unless I want to have a sandwich or a trim mean for some reason. Now, The dot dot, it so happens that that if you can create a advanced data type called diff time. That's not built into the language. It's built into the packages that are distributed with the language, and that gives you a an object that is a difference in time. It could be 3 days, 2 hours, 7 minutes, and 12 seconds. Whatever it is, it allow the what's called mean dot diff time allows you to specify the units of measure on the output. Now, the fact that it's called mean dot diff time, you probably will never see. You may see it in a diagnostic message. It's important to note that even though the identifiers in R, which are mostly variable names in our case, can include underscores or dots. The dots can't be in the first, the underscores can't be in the first position. Please don't put dots in the first position because that means the variable's hidden. And you can set it, but you'll have a hard time finding it again. Those dots are those were kind of long before dots were more or less universally the selector or the selector of attributes or the selector of subtypes. So it's just by convention that you'll see something like mean dot diff time. Old identifiers, things that have been around a long time, will be na.rm. There's a movement afoot to make some of them underscore, and you'll see more and more of those. But really no difference. My recommendation is if you're working in some set of packages, follow what's there. If you want to be modern, use the underscore. Okay, so back to so that's functions. That's how you call a function. These functions, you can also create a function. Now, a function, in the R language, everything is an object, and functions are so-called first-class objects, which means you can do anything with them that you can do with any other data type. So the way you create an object or a function is to name it, create your own function signature, and if you got more than one thing to do, put it in the same squiggly brackets we talked about earlier. Here's an example where we do have a optional variable. And if I try to add an nchar, by the way, another difference between R and Python is that length always gives you the length of a vector. If the vector happens to be a vector of strings, that is type character, if it's a single 20 character string, length is always going to be 1. You want to get the number of characters, it's nchar. Likewise, there are functions to extract substrings from strings. But at the moment, if we said, if you try to take nchar of null, you'll just raise an error. And if you want to make sure, it's not, and if it is null, it means someone declared it to be null, or it was or only one argument was specified. The last object that you name is the result of this function. Or you can explicitly say return result. Is that right? Or the return, I take it back. You can explicitly say, I'm going to fix that. You can explicitly say return open parentheses, result close parentheses. I'll fix these slides before I share them. And here we have, if we do these two calls, I won't do it for you, but one will produce 2, 4, 6, 8. Well, this will be one. V will be one less than the U, of course. Debugging functions. the easiest way to debug functions when you're starting off is to use the word browser. Now that word was picked long before before the web browser was imagined. So here we have a program. Oops, I was going to save it. That's just my habit. And I say run it. I'm going to clear that out so we see what happens. Oops, I'm going to run the whole thing. And there we see it prints by infini. I didn't, if I actually save it and then run it as, and we should probably pick a good name for it, but we'll just call it unsafe. Don't do that at home, folks. And if I source it, there it goes. If I say source without echo, I'm going to take it back and did it anyway. If I want to break it right here to see what's going on, I can say browser. And you see there's some optional stuff there, condition expression that I can say break if I did it the 100th time, something like that. Now if I run this, this browser. If we take a look again at what I can do with that, darn it. I can continue, I can quit, I can show where we are in the stack. So I'm going to say where. And then I'm going to say continue. Finish. However, as long as I have this, as long as it's not, I can also put a breakpoint here that's managed by RStudio. There's some real advantages to that because you don't want to get your program just perfect and say, no, all I have to do is remove all this debugging stuff. So you've made a change after you've tested it. And there's some other nice stuff you can do with this. But in particular, let's go back to so here's something that happened that in particular, I'm going to go back to the question of a function call. Now, this is not quite as fancy as VS Code, although it's really taken over the world for just about every programming language that it is. I can tell you with certitude that RStudio is still a dramatically better way to program in R. If we say function f is a function with one variable. The variable is s for string, and it could be one line functions, small ones. Maybe you don't have to make that break point, the block squiggles. So we're going to say return and char of s. It's not really a very good function. Why? Because if I inadvertently put something other than an s, there's my own private purposes, it's fine. But so I'm going to say I have to execute it. When I execute it, what I've done is to assign to the variable f the name of this function. And by the way, let's stop what I had. That just gave me a cue. And there's the function. By the way, and this is a really interesting thing when you're trying to learn more about R, or you want to understand why a function doesn't work. That word mean, that's just mean with parentheses is a function call, but mean is an identifier. There's the name of the function. Well, it so happens that that's a compiled function. But if I, and that's what this bytecode thing means. But if I said LM is as well. And LM, which is the linear regression that we ran an hour ago, all of the source code's right there. It's quite amazing. Now, the underlying computation, it's still compiled, but the underlying computations will be the underlying computations, what we're going to call, you know, the linear LM stat, LM stat, LM pack, the linear algebra pack that was all those decades ago written in Fortran, still runs the engineering world. But so I want to make sure that I've got it defined. I'm going to say f of XYZ. And you know what? It's not just a value that's going to otherwise ignore. So I'm going to say print f of XYZ. And what they're going to do now, it's going to, it printed the 3 because, why? Because 2 does not equal 3. Well, what happens if I put a breakpoint here? Actually, what happens if I remove all this stuff and then put it, no, excuse me. I do want to do that. I want to put a breakpoint. I'm going to put this back so I can put a breakpoint here. What if I put a breakpoint here? It says the breakpoint will be activated when the file is sourced. So it doesn't know, it knows that this will become a function, but it isn't one yet. So I'm going to save it, run source, and there we are at the breakpoint. One final thing to show you, this is super important. When you're debugging stuff, there is, I didn't have any other variables, so it doesn't look like much. There's the function, there's the database, there's the variable name, the variables I had when I started running, but I'm not there anymore. I'm up here. Here are the variables I have now that I'm in the middle of this, executing this function. And I've got S as a promise. I can look at S if I want here. And it's limited. And now I have something more of a mess because it's gone into the, S single step, that it was a bad name for the variable, I guess, which is another caution. At any rate, so important point is that the functions hide, when you call a function, the underlying variables are hidden, and you get a new symbol table, so to speak. And every level deeper you go, there's another symbol table. And each one of them is going to show up in this drop-down list. There is a way to get to the underlying global variable. Don't ever, it looks like this. Don't ever use it. It will create bugs for a generation. And that advice is canceled once you get a job with the R core group or something. Finally, on this topic, and this, in a sense, this is finally on this topic, iteration. So our motto in the world of R is vectors, yes, loops, no. There are times when loops are useful or even appropriate. For example, you're printing out you're generating 5 plots, and you want to and it looks like this, and 1 through 5, and you're going to say, plot something. It'll loop through as you might expect. Likewise, you can say repeat, And then it'll go until the cows come home. Until it'll go forever unless you have a break. We don't call it break. We call it break in here. And then the while loop is a for in it. But instead of saying, there was a very good book by some very good statisticians about it was something about bootstrap methods in R, and they were very good statisticians, but I think they were on their own for R, and so they did this. They said the result equals numeric. They said that n equals 10,000. And they said R is 1,000 zeros. And then they said for I in 1 to 1,000, R sub I equals R norm. That's doomed. And it works, kind of. It does work. It's not very fast. And if I said, do a histogram of R with 40 breaks, well, it's not very smooth, but then 1,000 isn't very many. If I did that to 1,000,000, I said 1,000, we should have said that in here. If I do it to 1,000,000, I think it'll take equals 10 e to the 6th. It's chunking away. It took about a second. And I should probably get something a little smoother when I plot it, I hope. Oops, where did the plot go? Oh, histogram. It isn't, that's nice. What I should have said was replicate my norm. That still takes a long time. Actually, it actually take a little bit longer in this case. I'm not quite sure why, but if I have if I have something complicated here, I don't need the loop. This replicate will return the vector. And if I actually took the time to read the instructions, I would say R norm n, the number of observations, R norm 1,000,000. Wow, can't even see it. Pause. And then of course, likewise, 2 or 1 or 2, then I'll say, oopsie, there's still R1. Now, one other thing I have to tell you is, so anyway, so that's what you can do with loops, and that's why I said apply, L apply, M apply. Here's those are functions that will apply arbitrary computations to, in the case of apply a matrix, in the case of a list, in the case of in the case of L apply a list, in the case of M apply a list as well, but in the case of L apply, you feed it a list, and it'll take the elements one at a time. In the case of M apply, you feed it 2 or more lists, and it will take those lists as the elements of those lists as a tuple, which basically represents the arguments to the function. You need to make these your friend. There's several other versions of it. They could be a little bit unsettling, but they're definitely worth knowing, and they keep you away from loops. Now, there's a few things about, we're not going to talk too much about graphics, but but there's plenty of ways to read and write. You saw at the beginning, we read a CSV file, we can read tab files. Special purpose packages can let us read all sorts of XML and all sorts of bioinformatics stuff, from FASTQ files to BAM files. Save and load RDS save a data set, R variable, which was possibly very large or possibly a complex object with with a bunch of structure in it. Saves it to a file, and load brings it back. There's a very interesting package called Shiny, which I am not going to get into today, and which I'm no expert, which allows you to make really beautiful web applications in R, and not really to replace the kind of, to build a site for buying your dog food on the web or something, but they're a way to interact with the user in a modern way. And parenthetically, there's some new technology that allows you to actually run R on the browser. That's just getting going, though. Graphics, we've seen two kinds of graphics today. One is not very much of either. One is our base graphics, which is plot. I show histogram. It's a version of plot. There's plenty of there's dozens of flavors of plot. It allows you an enormously strong level of control over what is plotted, where, and how. It will keep you in good stead with virtually any academic journal, or even non-academic journal, I suppose. And lots of the older packages, that's all they use. There's a totally different scheme called ggplot2. GG stands for the grammar of graphics. The very first plot you saw was a ggplot2. ggplot2 has grown over time. Let's go back to that. Is it right here? What the heck? Oh, I made a mess here, sorry. ggplot2, I loaded ggplot2 as the very first thing we did. And what it does is it builds up from a bunch of small pieces of the whole plot. This ggplot gets you started. It says, here's where the data is. This AES thing tells you, this is where I kind of messed it up. Let's go back to what I had it. The AES says, that's the aesthetics. It says what to pull out of the plot, color, and some control information to send down the line. Geom line is one of dozens of different kinds of plots. And then there's qualifiers, change a scale, put a title on, all sorts of things. It's super automatic. It looks pretty good. It's not quite as, and when you see this, you may say, I've seen stuff that looks like that, maybe in the New York Times or on television. That's because lots of people are using ggplot2. You get a really good result out in a short period of time. If you have to follow some strict rule because you're writing a dissertation or or it's going to be in, the Journal of the Black Tongue Disease or something. You're just going to plot may be better. And there are certain things like certain kinds of heat maps that are just much better with plot. I'll leave it at that as general guidance. And give yourself time when you want to dig into ggplot too. It doesn't come overnight. Just a second. Cut it out, Bob. There. Literate programming means is the idea that was first put forth by Donald Knuth, one of the greatest computer science educators of all time, in my opinion, is the idea that instead of just exploring the data, exploring the program, not just a statistical program, but any computer program, write the narrative of what you're doing while you're doing it. So this is combining the story with the code itself. It's probably familiar to a lot of you as a Jupyter notebook. In R, there's something called RMD, and R, that's R Markdown, which is like a notebook. It works really well in RStudio. Jupyter now has R support, but it's okay if you have to run some R. It's not so good if you've got to do some debugging. And finally, Quarto is the successor to Bookdown, which allows you to do this not only to do literate programming, but take it all the way to a finished book. The introduction to data science, for example, that I recommend you take a look at, is written in Quarto. You can take a look at the GitHub for it, I think under Rafa Lab, I believe, and see how it's done. If you're doing a study that you want to where you want to preserve the results of your exploration, RMD or Quarto, RMD particularly, or Quarto are great ways to do it. The packages come from lots of different places. I said, CRAN, the R comprehensive R network is got 20,000 of them. Bioconductor has 3,000. Posit has many of their own. And you can get them from GitHub or elsewhere. The ones that you don't get from CRAN, Bioconductor, or Posit are not necessarily QA'd the way the rest of them are. And one other thing that requires that I really ought to talk about is the tidyverse. The tidyverse is highly advocated. If you want to learn about the tidyverse, finish that volume 1 of the Introduction to Data Science. There's a lot about the tidyverse in it. The tidyverse starts with the idea of a data frame, extends it in a way to make it a Tibble, which is upward compatible from a data frame. And it uses what's called fluid programming, where instead of saying computation, make that variable A, variable B, it's computation of variable A, computation C is a computation of variable B. It has the idea of a pipe, which in the last year starts to look like this digraph, and formally look like this trigraph, which says, here's a computation, the output will become the input to the next computation. The best use cases for it are data wrangling and things that involve just transformation of what amounts to, spreadsheet style data. It's not, it doesn't have any support for matrices or for multidimensional arrays, whether you want to call those tensors or just arrays. But what it has done is to standardize a lot of data cleansing and data transformation use cases that were previously done with just kind of a wide range of somebody's using a for loop, someone else is using a lapply, someone else is doing some cool magic with a recursive function. So it's important to know, but it's also important to know where the main body of R is, the main body of our code, which is pre-tidyverse. And also that tidyverse is under rapid evolution. So there's something called Chrome, it's bio-tidy or tidy bio conductor. I can't think of it at the moment, but there's a major effort to transform the most important bioconductor genomic objects into this tidyverse format, so it can be intermixed with other tidyverse code. That's a very interesting idea, and it's useful, but again, it's at some point, if you want a matrix, and we didn't talk about it, but there is matrix, pretty nice matrix algebra in our it's that's going to be the limit of its use. So I wouldn't you it's again, I guess the best advice is to finish part one of the Introduction to Data Science book that I recommended. We have a few minutes left, and if anyone has any questions or comments, I'd be happy to take them. In famous speaker school, they said, well, you stand and raise your hand and kind of look everyone sadly, and then someone will come up with a question. But I don't think that works on Zoom. Does anyone have a topic that of the many topics I glided over? If anyone has one that they'd like a little bit more explanation on, or something that they don't think I described correctly, please, I'll be happy to take that too. If not, I can say that we can close out this session. I always was annoyed when people said, and we'll give you 7 minutes of your day back. That's not really true, but at least I'll give you 7 minutes. I'll give you 7 minutes without me, at least. And in the meantime, I will leave this because we have the room till noon. I'll leave, if it's okay with Erica and Anne, I'll leave this. I'll stay on until noon, and if you want to have an informal chat that we could have had if I hadn't come down with a cold. Thank you all for being here. And again, I'll be here for another 7 minutes.